So the last thing in this unit is to talk about power. Remember, it's WEP, right, which is work, energy, and power. So the last thing we're here to talk is to address this concept of power. So power, all right, is the amount of work done in a given amount of time. So again, if you see another way to think about it, anytime you do something in time, we call it a rate. So power is also defined as the rate at which work is done. The symbol is a capital P. The formula is power equals work over time. And we'll get it. Let's talk about the relationships a little bit, right? Because that's important here in this last bullet point before we do the first two examples. So you can see that power is directly proportional to work, okay? Which means if I increase the work, I increase the power. Okay, now here's the important one. Power is inversely proportional to the time, which means if I decrease the time, so this goes down, power will go up, okay? And a lot of times they'll do that on multiple choice questions or learning catalytics, just talking about these relationships. But you can also see that because work is force times distance, right? So power could also be written as force times distance over time. You'll see that power is also directly proportional to force, but it's also directly proportional to distance, right? So they may try to trick you into a relationship in that sense, okay? Now, the unit for power is the watt, W-A-T-T-S, right? The symbol for watts is W. It's named after James Watt, okay, who worked with engines, okay? Which, if you think about it, a more common unit for power is horsepower, okay? So when Watt was selling his engine, he had to go to farmers and say, hey, look, I've got this machine that can replace that whole barn of horses, okay? And so this is kind of where that unit came from. And the conversion factor between horsepower and watts is 1 HP is 746 watts. And one thing to note, if you get an energy bill, they'll talk about like kilowatt hours. So that means 1,000 watt hours in a way. And that's how you're charged, right? So if your energy bill says 9.2 cents per kilowatt hour, that means every kilowatt hour that you're spending or that you're using, okay, you're going to get charged 9.2 cents. And this kilowatt hours is not necessarily the unit for power. It's actually the unit for energy consumption. Right, so I'm consuming this much energy. Right, and again, like I said, that's how you get charged on energy bills. Okay. Now, go back to this next statement. It really talks about the relationships. So when you're climbing a set of stairs, right, you're going to do more power or generate more power when you run up the stairs versus walking up the stairs. Why? When you run, it takes less time, okay, than when you walk, right? And you go to the relationship. If I decrease the time, I increase the power produced, okay? Now let's look at just a couple examples using this very basic power equals W work over time formula. So you have a small motor running a lift that raises a load of bricks weighing 836 newtons to a height of 10.7 meters in 23.2 seconds. Assuming the bricks are lifted with a constant speed, what is the minimum power produced? Or what is the minimum power the motor must produce? All right, and so we're going to do power equals work over time. And now you have a couple options, right? I can come over here to the side and say, okay, well, work is going to be work times equals force times distance, and do 836. I wrote 863, right? And so I can just say, okay, it's going to be 836 newtons times 10.7 meters, and get a number. Plug that number in over here for work, or I can just simply substitute in my formula for work, and where I'm going to put the FD, the force times distance, in my equation for power, and then substitute in numbers. Okay, And so no, 836 newtons is about 83.6 pound or kilograms, which is about 170 something pounds. And so look at how much power needs to be generated by this motor. Surprisingly enough, it's not a lot. Okay, that's 386 watts. Right now, sometimes they may ask you to convert this to horsepower, and so you just say, okay, 1 HP is 746 watts, which is going to tell you that this motor is 0.516 horsepower, which is a very common motor, especially if you like a pool pump. Okay, pool pumps have motors on them. Okay, and they're really, you can get a quarter or a half, 1 or 1.5 horsepower motor to run that pump. Okay. Next one, the average power output of the human heart is 1.33 watts. How much energy does the heart produce in a day? Okay, so remember, work is changing kinetic energy, which means obviously just really the change in energy. Okay, and so what I can do is make that substitution from work to energy into my power formula. Okay, so power is going to be energy over time. I just substitute this for energy. Okay, so it's going to be energy equals power times time. But you have to convert 1 day to seconds, because really 1 watt, right? So 1 watt is 1 joule per second. Okay, so I need my time measured in seconds. So 1 day, right? There's 24 hours in a day. All right, you can go to the minute route, but you can go say in 1 hour there's 3,600 seconds, which tells me that there's 86,400 seconds in a day. Okay, and so then I just simply plug in my numbers. I got 1.33 watts times 86,400, and it tells me that the human heart generates 1.14 times 10 to the 5th joules of energy in a day. Okay, so that's just your heart. So you can imagine if you exercise a lot, you need more. That's why calorie intake is important for people. Why some people eat more than others. Okay. All right. Now, one thing about the power equation. So if I look at power, right, and we know it's work over time. Sorry, let me start with that. So we know it's work over time, but it's also force times distance over time, right? If we substitute in the work equation. But then also note this. If you remember way back in unit, what amounts to the second half of unit 1, well, distance over time is speed. So power is also force times speed. So what does that mean? It says to maintain a constant speed, an engine needs to exert a constant force equal to the combined effects of 3 things. And those 3 things are friction, gravity, especially if you're going up hills, okay, and air resistance. Most cars are not aerodynamic to the point where you can ignore air resistance, but so the force that we have to do to maintain constant speed has to essentially cancel out those 3 factors, which tells us by this formula that power is also dependent on 2 things, right? Or 2 other things. One is that constant force we just talked about, and the other is the speed of the object, okay? And you can see right here, power is F times V. Now, so that means we can write the formula, power equals FV. Now I'm going to write this in kind of a bracket. I know I didn't write it in the notes, but if the force is exerted at an angle, okay, you have to bring that angle into play. All right. So the next example says that it takes a force 1,200. It takes a force 1,280 newtons to keep a 1,500 kilogram motor moving with a constant speed of a slope of 5 degrees. If the engine delivers 50 horsepower to drive the wheels, what is the maximum speed of the car? Okay. So there's a lot of numbers in here. Really, the only 2 numbers that you need to worry about are this constant force we have to apply and the horsepower. This 5 degrees has nothing to do with, okay, the power generated, because it tells us that 1,280 newtons, right? If we're traveling at constant speed, eliminates any effect of the angle or the mass, right? And so we're just going to use our new version of the formula, power equals FV. But one thing we have to do before we can plug in is it tells us that it takes 50 horsepower. Okay, we need this in watts. So 1 horsepower. So 1 horsepower is 746 watts, which tells me that 50 horsepower is 37,300 watts. Okay. Now we're looking for speed, so we need to solve this for V. So it's going to be power over force. And so we got 37,300 divided by our force, which is 1,280, which means the maximum speed that this car can maintain in this situation is 29.1 meters per second, not squared. Sorry. Okay. Now, sometimes they may want you to convert this into miles per hour, because we're talking about a car, we're here in the United States, right? And so you have to do 1,609 meters is 1 mile, okay? And there's 3,600 seconds in 1 hour. And so if I do this quick calculation, it's 29.1 times 3,600 divided by 1,609. And so that's about 65 miles per hour. It's officially 65.1 miles per hour. Okay. Now you do have to, again, you have to be careful because Quest may ask for that, or tests may ask for it in miles per hour. Okay. Now the last example says you push a 67 kilogram box across the floor where the coefficient of kinetic friction is 0.55. What the force you exert is horizontal. How much power is needed to push the box at a speed of 0.50 meters per second? So again, the recommendation would be if you need some help identifying what is, what's the force and everything, okay, you can draw a free body diagram knowing that this is an applied force, right? And then you have friction going the opposite way. Now you have to, and then we want to finish out the free body diagram. Here's my force is acting, okay? So to maintain this 0.5 meters per second, we have to overcome the friction. So we have to, at minimum, apply the friction, which means we're going to do mu mg. So the coefficient times mass times g, because that is the friction formula. So you can see how all this stuff just, again, becomes reconnected, right? And so if I say power equals FV, right, because I'm going to use the force times speed version, well, my force is going to be mu mg, and I'm going to multiply that by V. So now I'm just plugging in numbers. 0.55 times 67 times 10 for simplicity times a half meter per second. And I'm going to have to do 184 watts of power, which kind of in the grand scheme of things is not much, because if I do the quick conversion factor, 184 watts, right? So 1 horsepower is 746 watts. And so that's going to be 184 divided by 746. And that's going to be roughly a quarter horsepower is what I have to generate to push this box. And that's not much. I mean, a pool pump does that, right? And so you can see there's multiple conversions there, because they do like to, Quest and tests like to kind of mess around and ask you to report answers in different units. But so that concludes unit 3 here, talking about WEP, work, energy, and power.